I like that.
Alright, so I'm Jason,
And I'm Ben.
and our project is the wireless signature recognition and sound manipulation device.
We'll get into that confusing title some more.
So, about wireless signature recognition and our sound manipulation device. So, Bluetooth is a very common technology nowadays. A lot of devices are being created with it. It's just there. I remember I got my first laptop and I just said, put it in there. Who knows what it's going to be used for in the future. A lot more devices are just having that. And so it's just a really commonplace, and it's a good thing to learn how to use.
Recently, digital signal processing has been increasing rapidly with this technology, and the music industry is one of the places that's taking a lot of advantage of this. For example, a lot of even local artists are using DSP in the form of effects pedals and synthesizers, other things like that, etc. So we decided to create a device that combines Bluetooth technology and DSP and motion sensing. We're going to use air gestures to manipulate the qualities of sounds and other signals.
So this is just a little general picture of what we just talked about. You have a guy sending something to a sensor bar. That device, that's sent through Bluetooth to a computer. That data is sent out to two other computers, manipulated. You hear the sound, you hear something else, and that's pretty much it as right now, but we'll get into the details shortly. So our approach, we used the Nintendo Wii Remote because essentially all of the sensing devices that we needed are on board. You also have the Bluetooth built in, which is how it communicates with the console. And so instead of finding a device that, a microcontroller or something where we would have to probably get the devices individually, we just got this and tried to use all of it at once.
Okay, for the manipulation of the sound and the data, we decided to use MATLAB because of all the reasons that the last group said. Basically, I can perform high-level calculations quickly, and to substitute the things that it could do in C would take a lot more lines of code, a lot more headaches, and a lot more sleepless nights, I suppose. And one of the good things about MATLAB in relation to what we're doing is that it has its own sound recording toolbox where you can record, manipulate, and play back audio all inside of MATLAB, so we can analyze the data and do everything we need to all at the same time.
So I'm going to start off with the peripheral software. This is not what we wrote, but this is what we used to control what was going on in the background. So the first and most important is connecting to the remote itself. I remember I started and I tried looking just for any way of connecting it to the computer, and in my process of finding this, I found a bunch of software that fell into two categories. Ones were complete programs with graphical user interfaces and everything, and then you had another type that was complete or sometimes incomplete libraries that had all of the drivers you needed to communicate with it over Bluetooth, and maybe sometimes it had an example or something like that. These libraries were usually written in C, Java, somewhere in Python and Perl, but we decided to use a library written in C because C was probably the strongest of the languages that I knew in comparison to the others, and C was actually just gets down there. So we used a library called WeUse, and one of the reasons why we chose it is because it supports IR tracking and motion sensing. So we actually used a version of WeUse that was what is known in the software world as forked, meaning that someone had created the software, another person, it was on the internet, someone took it and made modifications, and the modifications were so great that it actually was a distinct piece of software. And at that point it's considered forked. And sometimes what they do is they post it on they make it public so other people can see it and change it and modify their own version and fork it themselves. And this is really important because it's the basis behind open source software, where people create something, they edit it and make it better or sometimes worse, but the important part is that you're not recreating the wheel. So very critical engineering thing I learned. The GitHub is a forking community on a website, so someone starts it, they other people contribute, they edit it, and put it back onto the website, and everybody can see it. So it's a nice community effort. The version of we refer to it as our public because that's the user on GitHub that we got it from. His includes a bunch of source files as well as an example C code that demonstrates how to access the buttons, the sensors, and all the whiz-bang stuff that we wanted to use. Another part of the peripheral software is the operating systems and the Bluetooth. So we use this build to work with Windows, Mac, and Linux. We're having it talk to a Linux machine, but you can have it talk to all three of them, actually simultaneously. But Windows requires a Bluetooth stack that it likes, and then you need Microsoft's development kit to compile the code and to work with it. Mac, you need a 10.2 or greater. That's because that operating system has the Bluetooth built in. And then Linux, the kernel obviously has to support Bluetooth, and then you need the Bluetooth driver called Bluesy. We'll talk about that later. And also Bluesy's development library, so you can edit the code and compile it yourself.
We actually attempted to get this to run on all three systems, but at the time we had a Wiimote. It was a newer version, the one, not the 2006 one, but it had extra accelerometers and extra chips, and just it was more accurate, but it had a lot of connectivity problems with Mac and Windows. So we ended up doing Linux, but then we switched over to an older Wiimote, and the connectivity problems went away, but we already did the whole project, so we just stayed in Linux.
So yeah, so a little background about the Bluetooth stack. Bluetooth stack is like your internet stack. You have different layers between what goes on, but this is more geared towards Bluetooth, and it allows devices to connect to each other, talk to each other, and send data. And the Bluesy is the stack for Linux. It's flexible, allows computers to work, and it's built around the specifications by the Bluetooth Special Interest Group. We use Linux, like I said, but it just turned out to be the best way to do it. So the C code gets the data from the Wiimote and then sends it out to to MATLAB and stuff. But the way it does that is through UDP, which is User Datagram Protocol, and that's one of the most popular forms of protocols out there on the internet. So essentially, we're just sending it on the internet, and initially we just wanted to send it back to the original computer, and that's how we thought of doing it. And then in the process, it just made it seem so obvious to send it to another computer, and makes the whole project a lot more complicated and interesting.
So when we were using MATLAB, we decided that we wanted the user to know where they were with their air gesture, so we wanted real-time feedback, like a cursor of sorts. And we also wanted to analyze the code and search for patterns that it could be recognized, that we determined, or predetermined. But the thing about MATLAB is it runs commands linearly, and it can't process these sounds and use its sound recording and give you real-time feedback of where you are with your gesture. So we decided to send it over 2 UDP ports to 2 instances of MATLAB, so that one could give you the cursor and show you where you were, and the other one could be used to analyze and manipulate all the sound.
So this is the diagram we showed you earlier, though now we can really explain it. So we have the sensor bar, which is really mislabeled because it's not a sensor. It sends out light, and the Wiimote itself actually does the sensing. So, but then it gets the data. It gets it as X and Y coordinates. It sends it to the Linux machine. Linux machine does whatever it does and forwards it to the MATLAB, and MATLAB then has to parse the string that it sends and gets the data, plots it, and does whatever. So now moving on to the hardware. There's really not much to say about the hardware until we get to troubleshooting, but just to let you know that the way that the original Wiimote had it, it was a Broadcom system-on-chip Bluetooth device, and it works by using HID reports. In essence, in a nutshell, it's you have a report ID and you send it out. It's somewhat like a register ID, and then you accompany that ID with data, usually 1 to 2 bytes, but in some cases a lot more. And it goes out and it fills up register like it was an MCU. There are actual registers on the Wiimote, but we never really got down that low to actually having to use it because all the things we really needed were taken care of with the reports, and so it just didn't have to go down that far as research was concerned.
Okay, so signature recognition was one of the main things in our project. We wanted our program to be able to recognize if you made a shape or a gesture, like a swipe or something like that. So we had a lot of different ideas of how to do it, and we actually went through a lot of failed attempts at first. But the first thing that we decided we wanted to try to do was get MATLAB to recognize a loop. So initially,
so this is the first idea. My thought was apply statistics because you want to try to find some sort of match something. And so a linear regression popped up, and for those who are not really familiar or haven't seen this in a while, you get a bunch of data points, and linear regression tells you how close you are to matching a line. So we applied this concept to thinking we can apply to an arc, and it turns out you can do that, but there are constraints on the data points. It actually really needs to be very close to a perfect circle, and the problem with that is that the data is coming in as a handwriting motion, so you can't really rely on a person to give an accurate circle all the time, and it varies from person to person, even the person itself. You might draw it one way one time and then another way another time, so it just wasn't reliable to code it.
Another thing we attempted to do was quadrant detection, which is we were going to have a relative axis depending on where you started. There's 4 quadrants. And judging by the slope of how, if you started here and you were going in this direction, x would be decreasing and y would be increasing. So you know that you were in quadrant 1. Then if you came over here and you were going this way, x would be decreasing still and y would also be decreasing. And if you traveled around the 4 quadrants, you knew that you would make a circle. But the big problem with that was if you had like any little jostle in your arm or in your circle, or you made like a dip and then came back up or something like that, we couldn't think of an effective way to deal with that with the code without going through a bunch of headaches and hours of just headaches, I guess. So we ditched that idea. And then
so then a eureka moment happened when I was trying to sleep one night, and we came up with the solution that we're actually going to use, and that is to use position vectors. So your points are coming in, and I thought, well, just have a point from the origin go to that point, and therefore the point represents the vector. Then you have 2 vectors, and then if you take the dot product of those 2 consecutive vectors, you have the angle between them. So if you add up all the angles of all the points that you have, if it is a closed loop, you will get about 360 degrees, give or take a couple extra 10 degrees or so. But that was enough for us to say, well, hey, you got a closed loop here, so let's throw a flag and do something. So that's what we did. If you actually wanted to tell if it was a rectangle or a circle, you could apply extra constraints on it. For instance, if it was a circle, maybe check to see if the radius is consistent throughout some areas. But we just ran out of time for that, so we're just going to say we got a closed loop.
Okay, for the sound manipulation part of the project, again, we needed MATLAB to recognize these gestures, so we ended up going with this method, and we gave a little bit of a tolerance, but basically, if it was close to 360 degrees, we would consider it a closed loop. So MATLAB has this audio recorder function that allows it to record sound as raw sound data, and then we can manipulate the matrix that it resides in to put some effects on them. The ones that we ended up using were, that we got done were low-pass filters, high-pass filters, delay or echo, and sound reversal. and I'm going to show you the raw sound data and the frequency spectrum for each of these. This is the original sound that we recorded. I think it was something like, ooh, or something like, so we get some low and highs in there. So to do the echo and delay, we basically just had to record the sound, then take the signal and add it to itself at a later point in time. And that was pretty easy as far as easy goes. And that's the, as you can see, it kind of looks like the signals overlapped a little bit later in the raw sound data, and the frequency spectrum stays relatively the same. Sound reversal was also actually quite easy. We just had to flip the matrix so that all of the values were reversed, and that's just flip up down. So we did that, and this is the result of that. And then the low pass filter was a little more complicated, but I can explain this formula at the end if we have time, if anybody is very interested. But so we got it to work because, as you can see, the frequency spectrum, the low frequencies are raised and the high ones are cut out, and the oscillations are more slower. And the high pass filter, same thing but opposite. The lows are cut out, and that's the formula we used. This is the signal at a point in time -1 at, and there's only one column because we decided to do mono to simplify things, but we could have done two for mono and stereo, manipulated them separately if we had a little more time. So this is our time.
This is our timeline. Myth has it, a lot of senior designers don't follow this very accurately. Ironically, we have somewhat. Maybe not in the order that we have proposed in Senior Design 1, but believe it or not, we actually touched upon everything. So, and that's because we somehow made it so that we jump back and forth. We do some research, develop, test, we see if it fails, go back, plan again. And so that repeats a lot.
Yeah, design, research, develop, and review section. We weren't always researching the same project. We changed our mind a couple times, so that's a little not the way it was supposed to go, but we followed what it says. So.
Just not in the order. So this is, so you know, we did hit some hitches along the way, and that's why we had to go back and redesign. One of the things that really was annoying was that we initially had thought we were going to use accelerometers, so like we could have a shaking signature as well. And we were able to get accelerometer data, but it was just so much easier to just use IR data and work with that first. And time ran out, we couldn't get a decent signature from that. But so when that thought, we bought the Motion Plus that has the built-in accelerometers, thinking, oh, we're going to use this. And it turns out that that was a problem because it's the newer version, and because of the built-in accelerometers, the firmware has changed, and there's less backwards compatibility with the older remote. So one of the issues that we would have to connect 20 or 50 times before we actually got data to come through the computer.
And then when we wanted to change one thing in code, test it again, we had to try 50 more times.
Just to see what our change would do. So I mean, engineering-wise, you would think, well, we should sit down and figure out why this is not working. And we tried doing that to a certain extent, but since we were actually getting data, eventually we just said, well, let's work with what we got, and if we see a solution in the future, we'll do something. But fortunately for us.
What do you mean by building other code?
So yeah, because we were able to get data, we were able to build our MATLAB code to do what we wanted to do because we had some data to work with.
That's just a grammatical issue, actually.
Well, yeah, but we were still building it from scratch.
Building is a bit.
Yeah, I think that's a typo, actually.
Or a software.
I didn't catch that one.
That's fine.
So anyway, fortunately, a friend let us borrow the original remote, and lo and behold, it connects 1, 2, 3. We get the data when we want it. We're not waiting an hour just to get data. And so since we had that, we just went with it, and we've just been using that for the rest of the project. But we you know, we wanted to still figure out why the other remote wasn't working, and you know, I did some research and we found out that it's really not clear what Bluetooth chip the new one uses. If we change the slide. If on the left you see the original Wii remote, and I have labeled the Bluetooth chip, but on the right is the new remote, and most of the parts are lined up exactly on the same spots, and the Bluetooth chip is covered up where it should be. It's covered up by a black spot, and we suspected some sort of radiation shield or something to help the Bluetooth signal be stronger or something like that. But we're not sure because we didn't design it, so we don't know what the chip is.
Okay, and engineering constraints, environmental. We wrote this as if we would continue on this idea and build it up from scratch. And if we did, and we ever decided to mass produce it, we would use as many recyclable materials as possible. For the ethical things, we figured that it could be used for such applications as music therapy. It's a good creative outlet for people, and that's always good. Sustainability, we would extensively test it to ensure that it was robust. We want, if we put a product out, to make sure that it could last somewhere around 10 years. I know that's hard to come by nowadays, but we want to be different. Health and safety, we would include a Bluetooth radiation clearing device. Because there's some issues with Bluetooth and the things that it might cause, and there's been a lot of studies on it, but want to prevent that as much as we can.
So, in closing, we connect to the Bluetooth. We come up with methods to identify gestures. We did some extensive coding, working with the source code and with MATLAB. And then there are practical uses. One that comes to mind is if you have a hologram tablet, instead of having a stylus pen, you would have something like the Wiimote where you can, draw something with your finger as if it was a pen, and it would understand your signature without having to, touch down on something. And so again, there's room for future development. Maybe not using the Wiimote, maybe using a real MCU with real sensors, something else, but there's room.
We want to thank a lot of people. We want to thank Dr. Gonzalez, our advisor, Dr. Baziri. He gave us some tips too. The engineering department, Larry Capo, Tom
Walke, he's I've
removing
been on a couple
1,000
of
headaches. Thank you.
Yes, and SUNY Paltz for just being there for us, housing everything and whatnot. These are references.
Questions?
Questions?
I feel like that was confusing.
If anybody's interested, Ben could try to explain those equations from earlier if anybody's interested.
Do you have any demonstration?
Yes.
Maybe later on?
We have it set up for in the senior design lab.
Just because we have 3 different monitors, and it was just a headache to get it all down here, so.